Today we're going to work on solving equations. These equations are going to involve exponentials where the variable is in the exponent location, and or they're going to involve logarithms. So the directions for all of these will be to solve. For this first problem, I'm going to propose three different ways of solving. The first, the left side represented by y1 and the right side represented by y2. We're going to graph these and we're going to seek the intersection. When I graph these, I see that y2 is a horizontal line, y equals 5, and then y1 is an exponential function that is decaying because of the base of 1/2. We can find that intersection to occur at 6, 5. 6 is the value that we're looking for, so we would say our solution would be x equals 6. The other two methods are going to be algebraic, and we need to know at least one of these two methods. One algebraic technique would be to isolate the exponential portion. So isolate the 1/2 to the x over 3 by dividing by 20. What works out nicely for this problem is we get a 1/4. 1/4 can be written as a base of 1/2. We would have 1/2 to the x over 3 equals 1/2 to the second power. Because those bases are now the same, we can set the exponents equivalent. X over 3 equals 2, so x equals 6. This method particularly works out well because the 1/4 and the 1/2 can be written with the same base. That is not always going to be the case. A second algebraic technique that I'm going to show is to use a logarithm. So we have 20 times the base of 1/2 to the x over 3 equals the 5. I'm still going to isolate the exponential, but at this point, rather than creating a common base, because that's not always possible, I'm going to take the log base 1/2 of each side. So I have the log base 1/2 of x over 3. The properties of logarithms tell me that I could rewrite that as x over 3 times the log base 1/2 of 1/2 equals the log base 1/2 of 1/4. On the left side, I can simplify the log base 1/2 to the first power to equal 1/2, so I just get x over 3. And on the right, I can evaluate this. 1/2 to the second power would give me the 1/4. Multiply over the 3, I get x equals 6. We would need to know at least one of those two algebraic techniques. The second one has its benefits if the two sides of the equation cannot be written with a common base. This second equation is going to push our algebra skills. To solve, I'm going to multiply the 2 over to get rid of the denominator. I now am going to multiply every single term by e to the x. And the reason I'm going to do that is to remove the e to the negative x. E to the x times e to the x will give me e to the x squared. E to the x times negative e to the x will give me negative 1, and then 10 e to the x. I'm going to bring over the 10 e to the x minus 10 e to the x minus 1 equals 0. While this doesn't look like it, this is actually a quadratic equation. This quadratic equation doesn't solve, but if we rewrite e to the x as a variable w, or u sometimes is used, we would have w squared minus 10w minus 1. We would now see that quadratic function. If we could factor, that's great. However, we can't, so we're going to have to use the quadratic formula. W will equal the opposite of 10 plus or minus 10 squared minus 4 times 1 times negative 1 over 2. That will simplify out to be a w value of 5 plus or minus the square root of 26. We just solved for w, but let's keep in mind that this is actually equivalent to e to the x equals 5 plus the square root of 26, or 5 minus the square root of 26. E to the x is an exponential function, and an exponential function can never be a negative value. So 5 minus some greater value than 5 is an impossible value because that would be a negative. So all we need to do is solve e to the x equals 5 plus the square root of 26. The way we would isolate the x here is take the natural log of both sides. The natural log of e to the x will just yield an x. And on the right side, we'll get the natural log of 5 plus the square root of 26. In our calculators, we could say that that value is approximately 2.312 if we went to 3 decimal places. The great thing about these equations is for the first one, if I plugged back in 6, I would get 6 over 3, which is 2. 1/2 squared is 1/4, times 20 is 5. I can check that and I get a true statement. Same deal over here on the right. It's a little harder to plug in 2.312 or the exact value of natural log of 5 plus the square root of 26. But using my calculator, I could plug that in and I could prove that I have a true statement. We could check this e to the x minus e to the negative x over 2, graph that as y1, graph y2 as 5, and we could find the intersection of those two to be at 2.312, which would also help confirm a correct solution. We're going to move on to 2 more problems that involve logarithms. First, the log of x squared equals 2. Remember that the base that's assumed here, it won't ever be written, is a 10. For this problem, I'm going to use the fact that the log base b of a equaling x is the equivalent statement to b to the x equals a. The log is the exponent, and as a result, x will be my exponent. For us, 2 will be the exponent, and the base will be 10. So I could rewrite this problem as 10 squared equals x squared. 100 equals x squared. I could take a square root of both sides. When I take the square root, I need to remember to do plus or minus. I will get x equals 2 solutions, 10 or negative 10. And if I plug those back in, both of them would give me a true statement. One thing to be careful of, a little pitfall that we could have here, is if we did the log of x squared equals 2 and we applied the power rule to bring the 2 down in front, the log of x times 2 equals 2. Dividing by 2 would give us the log base 10 of x equals 1. 10 to the first equals x, and we would just get a single solution. What's happened is when we brought that 2 down in front right here, we actually changed the domain of the problem. Initially, the domain was all real numbers because we could plug in positives or negatives into x squared and get out a positive. However, when we bring the 2 down, we just have x as our article, and we could only plug in positives there. We're going to lose a solution when we bring that 2 down, so I would be careful of applying that power rule. The final question we're going to discuss here is the natural log of 3x minus 2 plus the natural log of x minus 1 equals 2 ln of x. Here everything has a base of e, and I'm going to use the properties of logarithms to simplify. I'm going to bring together the natural log of 3x minus 2, and I'm going to multiply that times x minus 1, and I'm taking the natural log of that whole product equals the natural log of x squared. Because we have the natural log of both sides, we could set their articles equivalent to each other. 3x minus 2, that quantity, times x minus 1 would need to equal x squared. Here I could FOIL 3x squared minus 2x minus 3x plus 2 equals x squared. One side should be equivalent to 0. Minus 5x plus 2 equals 0. Hopefully this factors. If it doesn't, I would have to use the quadratic formula, but it does. I get 2x minus 1 times x minus 2. That's going to equal 0. I'll get 2 solutions, positive 1/2 and positive 2. I need to be careful to always plug back in here and consider the domains. When I plug back in 2, I get 6 minus 2, I get the natural log of 4. I can evaluate that, but I would need my calculator. The natural log of 2 minus 1 is the natural log of 1. I can evaluate that. And then 2 times the natural log of 2, I can evaluate that, but I would need my calculator. However, when I plug back in 1/2, in particular, when I plug back in 1/2 into the natural log of x minus 1, I get the natural log of negative 1/2. I cannot take the natural log of a negative number. I can't take the log of any negative number. Therefore, 1/2 will be what we call an extraneous solution. 1/2 is not on the domain of this problem. This problem would only have a domain of 1.5 or greater, and that's going to be set by this 3x minus 2. The x minus 1 also plays a factor, but the 3x minus 2 is more restrictive. I'm going to leave you with 4 problems to practice along the same lines as the ones that we've just shown. Good luck.